In 2.5, we're going to be building up our justifications for what we're eventually going to be calling proofs in a big portions of other chapters. At the top, we have a few properties of equality which you've already used in algebra classes before, basically to solve equations. Things like the addition property, just saying that if I have two sides of an equation already being equal, I can then add a third value to both sides and they're still going to be the same. Same thing with subtraction. I could subtract the same value from both sides, the equation's still going to be true. I could multiply, I could divide, and these are all things we've seen before in terms of isolating usually for a variable when I'm solving an equation. We have some additional properties of equality called reflexive property, just something equal to itself. Think that like 5, for example, is always going to be equal to 5. I could also switch sides of an equation and have it still be true. So I could say x equals 5 or 5 equals x. Either way, that's usage of what we call that symmetric property. Transitive is kind of like my linking statement, saying that if I know that I have a connection between two values, a equals b, and then I'm introducing a third, so c is also equal to b. Kind of using b as our link between the two to say that from the very start to the very finish, starting from a and ending at c, those must have been equal as well. So for example, if I know that like a equals 2 and then 2 equals c, I know a equals c because they're both equal to 2. So substitution property is also we've been using in algebra before, just saying that if I know that a equals b, then b can replace, not c, but b can replace a in any expression that I have if it was longer than just those two. We've also seen the next property as well. So distributive is something we've had experience with before. We can use multiplication to distribute, and again, just by multiplying twice, we have two products, ab plus ac if I'm using addition, or ab minus ac if I'm using subtraction. Works no different if I'm using a sum or a difference. And besides those properties, we can also build them together and form things which we call proofs, which are essentially just justifying each step of a solution. And we just have to list our reasoning for each justification as we go. So that's what that little blurb is referring to down there. Again, we're justifying steps with postulates, definitions, or properties. We're going to be using a lot of these from our last two tables. So if I'm given a question like this to find the value of x and then justify each step, again, what we're looking to do is actually solving just like we would normally, but we're going to have to list the reasoning for our solution as we go. So when I'm solving this, again, this is something we could have seen on our last chapter test. We know that if I was to take those two angles and look at them as a pair, I'm just going to look through those justifications step by step. We know they're, I guess I deleted that part. We know they're supplementary because, again, the reasoning for them being supplementary is that any angles that would form a linear pair, which those two do, again, angles that add up to form that kind of a straight line or a linear pair, and they're a linear pair, again, that means that we know they're going to be supplementary. So if I know they're supplementary, that's going to lead us to my next step. Again, a lot of this you'd kind of do in your head as you're solving it anyway, but our next step is saying that if I know they're supplementary, that's how I know that they're going to have a sum of 180, again, because that's just true for any supplementary angles. And then now I'm getting to the algebra part of our question. We know that if those are going to add up to 180, I can then just take those expressions, again, as we would basically start this question, if I was just looking for a solution for x. And since I know that they are representing those angles, AOM and MOC, those two measures, I can then just substitute them into my equation using what we call just that substitution property. So after this, again, this is essentially an algebra solution. So normally we'd call this combined like terms. So I'd still accept combined like terms, but we could call that step in between distributive property. Again, just by taking 2x and x, adding that together to get 3x. From here, you can already kind of see that next step is going to be subtraction if I'm looking to solve for x. In this case, it looks like we'd subtract 30 from both sides. And then to finish, because we're still looking to isolate for x, we'd have to do that by dividing 3, if I can get rid of that, dividing 3 from both sides, and that's going to allow us to finally get to our answer that says that saying that x is equal to 50. So again, everything on the left-hand side we've basically already seen before, knowing that, again, if I add two angles together to make a linear pair, they're going to make 180. Then we can start with the algebra by substituting those expressions in and then working through our steps to isolate x. Only difference now being that we want to list our steps as we go in terms of what's the justification for each thing along the way. And again, if I am listing my justification, it's going to be using the properties that we've seen from before and we see up above in that table. So things like, again, substitution, subtraction, I can subtract from both sides, I can divide from both sides. All of our algebra steps are able to use anyway. We just want to list those justifications. So before, again, just kind of comparing our next few properties, we define these as properties of equality, just because we're using equations to make those properties. If I notice them all set up with my rules, we begin with equations. And when I have this next box listing properties of congruence, notice we've already seen these three properties before with equations. Properties of congruence is just to say that rather than an equation for properties of equality, we can use them for congruent statements. So now they're, again, properties of congruence. And I can use the same kind of terms as before. So reflexive property, remember from before, we said reflexive property just implies that something's equal to itself. And that's a property of equality. It's also a property of congruence because a segment that's congruent is definitely going to be congruent to itself. So we're saying that if I take the same segment twice, not going to be changing anything about that segment's length. Same thing with an angle. Angle is always going to be congruent to itself. And again, that's just an example of reflexive. Symmetric property, just from, again, the last time we said that I could just flip sides. X equals 5, 5 equals x is going to be an example of symmetric property of equality. I can then just take that with congruent statements. So again, symmetric property just means I'm kind of flipping the order from left to right, right to left. I can say two segments are congruent and then flip the order and say those same segments are still going to be congruent. And I can do the same thing with angles. If A is congruent to B, then I can also then just flip that and say B is congruent to A. Again, just meaning that these are still going to stay congruent. Transitive, remember, you want to think of this kind of like your linking property. If I know that AB is congruent to CD and then CD is also congruent to this third segment EF, that allows me to link from the very start to the finish because they're both going to be congruent to CD. We know that AB from the very beginning should eventually be congruent to EF from the very end. Same thing works for angles. If I know that A is congruent to angle B and B is used as a link to make that congruency statement congruent to angle C, then I know that again from the very start to the very finish, A should then be congruent to C because again they're both congruent to B. Easy to think about this if you just think about like a value, like let's say that A is like 20 degrees and that C is 20 degrees. I know that A and C are both congruent because they're both, of course, 20 degrees. We could also just kind of flip the order. Notice that this is like an example of symmetric property. I could flip the order as long as I still have that link. B is still congruent to both A and C. That allows me to say that A and C are congruent to each other. Again, you just want to think of that as kind of like your linking statement. So B in this case being used in both parts of those congruency statements. So I can use A and C being congruent to each other. So as we just list like one step, it's good to just kind of point out what property we're using on that step. So first one I have blank, but again, the other two might have an idea of what we're using for those. So the first example, a lot of people accidentally use like addition for this kind of question. They see something like +9. Right away they think like addition property. But the idea is, again, how do I get from the first step to the second? So if I was to get from that first step and let's say like work on a solution to isolate for x, we do that by subtracting 9 from both sides. So the property that I'm actually using here, even though we don't see it written anywhere in the question, is the subtraction property. And technically you could also say property of equality. But yeah, subtraction property allows us to subtract 9 from both sides, and that eventually would get us an answer for x. Here we can just list what's the step that gets us from, or sorry, what's the property rather that gets us from step 1 to step 2. So if I'm recognizing the next property, again, looks like it shows up above in my table. This looks like a usage of transitive property if you guys were answering that one independently. Yep, looks like it's going to be transitive. And transitive you just want to think of as your link. Looks like in this case W is linking O and L together as those two congruent angles. So if O is congruent to W, W is also congruent to L. That's where I can then say O and L are congruent from start to finish because we know they're both congruent to that same angle. So might look familiar with that next one. Again, this is some property up above that we see as a property of congruence. This looks like the symmetric property, again, because I'm just flipping sides, E congruent to T, T congruent to E. Just by flipping sides with my two, sorry, it would be this usage of my property. That's my example of symmetric because it doesn't matter if something shows up on the left or right side of a congruent statement. I know they're still going to stay congruent on either side. So this is all building up to, again, what we're going to be calling a proof. So two-column proof is going to be what we're writing in this class. And just to kind of keep track of what we're writing down for our statements and our reasonings here. Again, statements, kind of like we had up above anyway, basically working through the question on the left-hand side and then justifying those steps on the right-hand side as we work through that two-column proof. If you'd like to pause and make sure you get this down, again, it just means that we could have a certain starting point. First statement is going to be given from the question. We know that angle 1 is, not congruent. It is congruent, but measure is equal to angle 3. And we know that if we're trying to prove this statement, that's going to be where we try to finish. We don't exactly know how many steps it's going to take before I solve the problem, but at least we know it's going to come last in our statement because once I've reached that statement, that's what I'm trying to show. And if we've shown it, we don't really have to go any further. But as you're working through a proof, that middle section just saying each statement should follow logically from reasons I've already listed, which means I can't really list like a statement that depends on something that comes after it. We want to make sure these do follow in a logical order and just kind of working our way downwards through this proof. So we do have a couple examples below. Again, this two-column proof structure is literally as its names, like 2 columns for working through the question and then listing my justifications for it on the right. So if I was to start with an algebra proof, again, just trying to solve for x basically, as we would do in an algebra class anyway, we want to make sure I can start from that given statement. Again, first statement is what's given. So we can just start there. I'm just going to list it, statement 1, 5x plus 1 equals 21, exactly as we start the question. Reasoning, you don't have to do anything else besides that first part, given, so it should be kind of a gimme question. And then for my next statement, of course, I have to work my way through and isolate for x here. So if I was working through this in Algebra 1, I'd start by subtracting 1 from both sides. This time we just have to list our justification for it, so we already know this step. Now we just want to list that the reason why we're able to do that is that subtraction property of equality. And if I was looking to finish my proof, looks like it's only going to take one more step, so let's list this as statement 3. I think we could get there by eventually getting to x equals 4. Again, that's where I wanted to prove, so that's where the step that I'm ending on. And that statement, again, the reasoning rather, to go from step 2 to step 3 is by dividing from both sides. Looks like we divided 5, but we don't even have to list that. We just have to say that we know that we're using division to get from step 2 to step 3. So you do want to be careful. Again, a lot of people might list like division on the previous step. You only want to list a reasoning after you've used it to arrive at that next statement. So notice for the same reason, I didn't say subtraction for the step 1, even though that we knew we're using subtraction to get from statement 1 to statement 2. So again, you want to work through the statement in that order, then list why you're able to get to that step, and then continue through the proof after that. So we know that we start with a given statement. I know that to get to the next one, that would be our next step, and we got there by subtracting, so that's why I listed it on step 2. And then again, from step 2 to step 3, we got there by dividing 5, so that's why I listed my reasoning on that last step. That was just using division. So a good one to try is that next one. Again, another algebra proof, but I'll just kind of reveal these reasons as we go. First one, again, should be kind of a gimme, because if that's a given statement, that should be something that we start the question with. So I know that I can write the question exactly as it appears on that left-hand side. We're always just going to say given. Again, don't have to get too complex for that first step. Next step, again, if I was to solve this using my algebra, I would think about distributing to get rid of those parentheses. So now I have 3x plus 12 instead of, again, 3 times that quantity, x plus 4. And again, this time we just have to list the reason for it. As long as you remember that's called the distributive property, that's all you'd have to put on that line. So the next step, you could list a couple different things here for your reasoning, and I would accept it. If you said something like combine like terms, I get where you're coming from. 3x plus 3x does make 6x. In the book, a lot of times you're going to see this called distributive property, so I just listed that as well. But yeah, as long as you know that you're just collecting those 3x terms together on that left-hand side of the equation, distributive, combine like terms, I would accept all of that for reasoning there. For our next step, again, just kind of working your way through the algebra question solving for x, you would have to subtract 12 from both sides. Notice, again, you don't have to say that you're subtracting 12. You just have to say what property you're using, so that's the subtraction property. And I think we'd arrive at our proof statement with one more step, so notice that that's where we're trying to prove. That's our last statement where I finish. So if it got there, it looks like by, again, not dividing 5 from both sides, but you would have to divide 6 from both sides. You don't have to say divide by 6. You can just say that we're using the division property. Again, our reasoning is basically just what property justifies that step, not what is the exact step that we're taking. So to go from step 4 to step 5, we divided by 6. And since I divided, all we have to do is list that division property.